Hello, curious minds. What if I told you there's a place where time stands still and the laws of physics, as we know them, break down? Sounds like science fiction, right? Well, it's not. Welcome to the mind-bending world of black holes. So, what exactly is a black hole? Imagine a region in space where the pull of gravity is so strong that not even light, the fastest thing in the universe, can escape. A black hole is essentially a massive object compressed into an incredibly small area. This creates a gravitational field so intense that it warps the very fabric of space and time around it. Think of space-time as a stretchy fabric. When you place a heavy ball on it, the fabric bends. A black hole is like an extremely heavy ball creating a deep, steep well in this fabric. Let's break down the key components of a black hole. First, there's the event horizon. This is the boundary of the black hole, the point of no return. Once anything crosses this boundary, it cannot escape. It's a region where the curvature of space-time becomes so extreme that all paths, all possible trajectories, lead inexorably inward towards the singularity at the black hole's core. Inside the event horizon lies the singularity, the heart of the black hole. This is where all the black hole's mass is concentrated into a single point with infinite density. It's a place where our current understanding of physics breaks down. Surrounding some black holes is the accretion disk. This is a swirling disk of gas, dust, and other matter that spirals into the black hole, heating up and glowing brightly as it does so. Now that we have a basic understanding of what black holes are, let's dive deeper into the different types of black holes that exist in the universe. Black holes, as it turns out, are not one size fits all. They come in different varieties, each with its own unique characteristics. Let's start with the most common type stellar black holes. These are formed from the remnants of massive stars that have undergone a supernova explosion. When a star that is at least 20 times the mass of our Sun collapses, it can form a stellar black hole. These typically range from about 3 to 20 times the mass of our Sun. Imagine a star 10 times the mass of our Sun, compressed into a region the size of a city. That's the kind of extreme density we're talking about with stellar black holes. Next, we have supermassive black holes. These giants reside at the centers of galaxies, including our own Milky Way. They contain millions to billions of times the mass of our Sun. Their formation is still a mystery, but they play a crucial role in the evolution of galaxies. The supermassive black hole at the center of the Milky Way, known as Sagittarius A star, has about 4 million times the mass of our Sun. Then there are intermediate black holes, which are much less common and not as well understood. They have masses ranging from hundreds to thousands of times that of our Sun. These might form from the merging of several stellar black holes or from the collapse of massive star clusters. We also have the hypothetical primordial black holes. These are thought to have formed in the early universe just after the Big Bang from high-density fluctuations in the expanding universe. Primordial black holes could have a wide range of masses, from very small to very large, but there's no direct evidence of their existence yet. Lastly, there's the intriguing concept of miniature black holes, also known as micro black holes or quantum black holes. These tiny black holes could be as small as an atom, but with the mass of a large mountain. They are purely theoretical and might form through high-energy collisions, such as those created in particle accelerators, or possibly in the early universe. Miniature black holes would evaporate quickly due to Hawking radiation, making them difficult to detect. Each type offers unique insights into the workings of our universe. Now that we've covered the different types of black holes, let's dive into the techniques that allow us to detect them. Black holes, by their very nature, are invisible to conventional telescopes. After all, how can you see something that doesn't emit light? But fear not, for the universe has a way of revealing its secrets, often in the most unexpected ways. One such revelation came with the discovery of gravitational waves. Imagine, if you will, the fabric of space-time as a vast cosmic trampoline. Now picture a massive object like a black hole, rolling across this trampoline. As it moves, it creates ripples in the fabric, distortions that propagate outward at the speed of light. These ripples, my friends, are gravitational waves. These waves, predicted by Einstein's theory of general relativity, carry information about the objects that created them, much like fingerprints at a crime scene. And when two black holes collide, they unleash a cataclysmic burst of gravitational waves, a cosmic symphony that can be detected billions of light-years away. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting gravitational waves for the first time, confirming Einstein's predictions and ushering in a new era of astronomy. It was a monumental achievement, allowing us to hear the universe in a whole new way. Now that we've explored how we can detect black holes, let's dive into the incredible effects these mysterious objects have on their surroundings and the very fabric of space-time. The most prominent effect of a black hole is its immense gravitational pull. This gravity can have dramatic impacts on nearby stars, gas, and even light. When a star ventures too close to a black hole, The difference in gravitational pull across the star can stretch and tear it apart in a process called spaghettification. The remnants of the star can then be accreted by the black hole, forming a bright accretion disk. The accretion disk itself is another remarkable effect. As matter spirals into the black hole, it heats up due to friction and gravitational forces, emitting intense X-rays and light. Black holes also influence their surroundings through powerful jets of particles. In some cases, black holes can eject streams of charged particles at nearly the speed of light. These jets can extend for thousands of light years, impacting interstellar gas and even triggering star formation in distant regions. Another fascinating effect is gravitational lensing. Black holes can bend light from objects behind them, creating a magnifying effect. This can produce multiple images of the same object or create a ring-like structure known as an Einstein ring. Gravitational lensing allows astronomers to study distant galaxies and objects otherwise obscured by other cosmic structures. Black holes also play a crucial role in the dynamics of galaxies. Supermassive black holes at the centers of galaxies can influence the motion of stars and gas across vast distances. Their gravitational pull helps to maintain the structure and stability of the galaxies they inhabit. Moreover, black holes can merge with other black holes, or massive objects, releasing gravitational waves. These ripples in space-time carry information about the events leading to the mergers and the properties of the black holes involved. Gravitational wave observatories like LIGO and Virgo have revolutionized our understanding of these cataclysmic events. Finally, black holes challenge our understanding of physics, particularly at their cores. The singularity at the center of a black hole, where density becomes infinite and known laws of physics break down, pushes scientists to explore new theories of quantum gravity and the nature of space and time. Throughout the cosmos, stars are constantly being born and dying in a magnificent cosmic dance. We've talked about how some stars simply fade away, but others, well, they go out with a bang, a supernova, leaving behind a core of unimaginable density. Imagine a place where a teaspoon of matter would weigh billions of tons. That's the kind of density we're talking about. Now, when a star significantly more massive than our own sun, say, more than 20 times the mass, reaches the end of its life, it exhausts its nuclear fuel. The outward pressure from nuclear fusion can no longer counteract the inward pull of gravity, and in one final spectacular act, the star collapses in on itself. This collapse, this implosion, is so violent, so powerful, that it creates a region of spacetime so warped, so dense, that nothing, not even light, can escape its grasp. This, my friends, is the birth of a black hole. It's a cosmic monster born from the death throes of a giant star, and just like any newborn, it's hungry, eager to devour anything that ventures too close. But don't let the name fool you. A black hole isn't empty space, it's quite the opposite. A place where unimaginable amounts of matter are squeezed into an infinitely small point. We call this point a singularity, and it sits at the heart of every black hole, a point of infinite density and zero volume. The birth of a black hole is a testament to the immense power of gravity, a force so strong that it can warp the very fabric of spacetime. And as we'll see, this warping has some pretty mind-boggling consequences. We've learned how black holes can form from the collapse of massive stars, but there's another fascinating way they can be born. Through the collision and merging of two black holes. When two black holes orbit each other, they eventually spiral closer due to the emission of gravitational waves, ripples in the fabric of spacetime predicted by Einstein's theory of general relativity. As the black holes get closer, they merge in a spectacular collision, combining their masses to form a new, larger black hole. This process releases a tremendous amount of energy in the form of gravitational waves. So the collision is not just an end for the individual black holes, but also a new beginning, a birth of an even more massive black hole, continuing the cosmic cycle. With this understanding of how black holes can be born from both stellar collapse and mergers, we can now move on to the next chapter. Black holes constantly consume anything that ventures too close. Gas, dust, even stars themselves can become ensnared in a black hole's gravitational web. As this material spirals inwards towards the event horizon, it forms a swirling disk of superheated matter, what we call an accretion disk. Imagine a cosmic whirlpool, a maelstrom of gas and dust heated to millions of degrees by friction and the intense gravitational forces. This superheated material emits high-energy radiation, X-rays, and gamma rays that can be detected here on Earth, allowing us to indirectly observe these invisible giants. The accretion disk is a feeding ground for the black hole, a chaotic and energetic region where matter is constantly being pulled in and devoured. But the black hole doesn't swallow everything whole. Some of the infalling matter is redirected and ejected outwards at nearly the speed of light, forming powerful jets of energy that can extend for thousands of light years. These jets can blast through entire galaxies, shaping the evolution of galaxies and influencing the formation of stars. Black holes, despite their destructive nature, play a crucial role in the evolution of the universe. They shape galaxies, regulate star formation, and even influence the distribution of matter on the largest of scales. They are a testament to the interconnectedness of the cosmos, where death and destruction often pave the way for new beginnings. For years, black holes were thought to be inescapable cosmic traps, points of no return where matter and energy vanished forever. But in the 1970s, physicist Stephen Hawking proposed a revolutionary idea. Black holes aren't entirely black. They actually emit a faint radiation now known as Hawking radiation. This radiation, Hawking theorized, arises from the quantum vacuum, a sea of virtual particles that constantly pop in and out of existence throughout spacetime. Near the event horizon of a black hole, these virtual particle pairs can be separated, with one particle falling into the black hole while the other escapes into space. The escaping particle carries away a tiny amount of the black hole's energy, causing the black hole to slowly lose mass over time. This process is incredibly slow, especially for large black holes. In fact, the rate of Hawking radiation is inversely proportional to the black hole's mass. This means that smaller black holes evaporate faster than larger ones. Hawking radiation has profound implications for our understanding of black holes and the nature of spacetime. It suggests that black holes aren't eternal prisons but rather dynamic objects that eventually evaporate, returning their stolen energy back to the universe. So we've journeyed through the basics of black holes, their birth, their life, even their eventual demise. But some questions still make these cosmic devourers as enigmatic as ever. One of the most captivating is the idea of wormholes, theoretical tunnels that could connect different points in spacetime. Imagine for a moment the fabric of our universe as a piece of paper. Now fold that paper in half, so 2 points touch. A wormhole, in theory, would be like punching a hole through those points, creating a shortcut across vast cosmic distances. It's an alluring concept, a cosmic shortcut that could potentially allow for faster-than-light travel and journeys to distant corners of the universe or even other universes entirely. Now before you pack your bags for a trip to Andromeda, I have to tell you, wormholes are highly speculative. They emerge from the complex mathematics of Einstein's theories, but their existence remains purely theoretical. We haven't observed them directly, and the conditions required for their stability are mind-boggling, involving exotic forms of matter with negative energy density, something we've yet to discover. Still, the very idea of wormholes ignites our imagination, reminding us that the universe is full of surprises. Perhaps one day, our understanding of the cosmos will evolve to a point where these cosmic shortcuts become more than just theoretical possibilities. And if wormholes weren't mind-bending enough, let's dive into another captivating mystery linked to black holes, the possibility of parallel universes. The idea that our universe is just one of many, coexisting alongside others, has been a staple of science fiction for decades. But could black holes be the key to proving their existence? Some theoretical physicists propose that the singularity at the heart of a black hole, a point of infinite density, could be a gateway to another universe. Imagine it like this. If our universe is like a bubble, the singularity of a black hole might be a point where our bubble connects to another, creating a passage between these separate realities. Of course, the concept of parallel universes stemming from black holes is highly speculative, just like wormholes. We can't peek beyond the event horizon, that point of no return, to see what lies beyond. The extreme conditions near a black hole make direct observation and experimentation impossible, at least with our current technology. However, the very existence of black holes, objects that challenge our fundamental understanding of physics, keeps the door open for these kinds of mind-blowing possibilities. The universe has a knack for exceeding our wildest imaginations, and perhaps, just perhaps, parallel universes await us beyond the enigmatic veil of a black hole's event horizon. We've traveled a long road together, haven't we? And one thing is for sure. Black holes stand as a testament to the immense power and mystery of our universe. They are cosmic laboratories where the known laws of physics are pushed to their very limits, revealing glimpses of the strange and wonderful tapestry of spacetime. They remind us that the universe is far more complex and awe-inspiring than we could have ever imagined. And there you have it, the incredible journey of black holes. These cosmic enigmas continue to challenge our understanding and inspire our imagination. If you enjoyed this dive into the universe's darkest secrets, give this video a thumbs up and subscribe for more cosmic explorations. Have questions or theories of your own? Drop them in the comments below. I'd love to hear your thoughts. Thanks for watching, and until next time, keep looking up.